In this video, we're going to do some applications of conic sections. We're going to apply what we've learned to some actual real-life problems. First off, let's start with some circle applications. And if you don't remember, the equation of a circle, x minus h squared plus y minus k squared is equal to r squared, where the h and k shifts it and the r is the radius. On average, the circular, notice it says circular, eye of a hurricane is about 15 miles in diameter. So the diameter is 15, and that's in miles. With gale winds, that can affect an area up to 300 miles from the center. Now, you've got to be careful here. 300 miles from the center, that's going to be a radius of 300. So be careful with those two things. The landfall of the eye of a hurricane can be represented by this point. So that's the middle on a coordinate grid. Write an equation to represent the area of the eye. So it says the eye had a diameter of 15. Again, this was the center, so therefore A part. The eye of the storm has a location that's been shifted right 32 up 70, so that's going to be x minus 32 squared plus y minus 70 squared to move it up 70 is equal to, okay, it says again, the eye has a diameter of 15. So this is going to be 7.5, which is half of 15 squared, which is going to be 56.25. That's the equation of the eye of the hurricane. Now B part says write an equation for the area affected by the winds. The winds can affect an area up to 300 miles from the center, so a radius of 300. So the center is going to be the exact same thing. So you still have the x minus 32 squared and the y minus 70 squared, but it's going to equal to the radius squared now, which would be 300 times 300, which would be 900 hundreds or 90,000. So there's your two equations. Number two, the beam of a lighthouse can be seen for up to 25 miles. A boat is located 20 miles west and 18 miles south of the lighthouse. Write an inequality, not equation this time, but write an inequality to represent the region lit by the lighthouse beam. Well, the first thing we need to do is recognize, is this a radius or is this a diameter? It can be seen up to 25 miles. So it's shining from the lighthouse up to 25 miles, and that'd be 25 miles in all directions with the lighthouse at the center. So that'd be a radius of 25 miles. So the boat is located 20 miles west and 18 miles south. Write an inequality to represent the region lit by the lighthouse beam. So first off, it doesn't give us a center. So we're going to let the lighthouse be the actual center of this circle. And we're going to let it be located at the point 0, 0. So 0, 0 is my lighthouse. So x squared plus y squared. And then is equal to r squared. Normally we do equals r squared. So equals 25 times 25, which is 625. However, the beam can be seen everywhere within that region. Okay, not just at exactly a radius of 25, but even smaller radii, when the radius is 24, when the radius is 23. So x squared plus y squared is less than or equal to 625, where the radius is 625 or smaller. Is going to be all the places that you can see this light. So now what they're going to do is, what about this boat? B part says determine whether the beam can be seen by the boat. So you've got the lighthouse located at 0, 0. You've got the boat that's located 20 miles west, 18 miles south. So that's 20 miles west, 18 miles south, somewhere down here. At negative 20, negative 18 is the location of the boat in comparison to the lighthouse. What do we do to see if it can see this? We plug in negative 20 for x and negative 18 for y. So we have negative 20 squared, which would be 400, plus negative 18 squared, which is 324. Does that satisfy the inequality is less than or equal to 625? If you add those, it gives you 724. That is outside of that 625 region. It's too far out, so therefore, can the boat see it? No, it cannot. Next up, number 3, let's talk about an ellipse, and here are the equations for an ellipse. And just a reminder, with an ellipse, your A value is always bigger than your B value. The first one represents a horizontal ellipse where the bigger number is under X. The second one is a vertical ellipse where the bigger number is under your Y stuff. Okay, a glass window in the shape of an ellipse has a major axis of length 60 and an eccentricity of 0.7, which remember eccentricity is equal to C over A. Write an equation to represent the outline of the window. So what we're going to do, since they don't give us a center, we're going to let the center of that window be 0, 0. So therefore, H and K are both 0. Notice it's wider than it is tall, so that would be a horizontal ellipse. So that's going to be x squared over something, or over a squared, excuse me, plus y squared over b squared is equal to 1. So really all we have to do is find what is our a value and what is our b value. The major axis. The major axis is the length from here. Let me do a different color. The length from here to over here. That's the width of your ellipse. The a value is the distance from the center to the outside edge. So therefore, we have an a value here of 30. Since the eccentricity is 0.7, we can plug it into this equation. The eccentricity of 0.7 is equal to C over 30. When you multiply by 30, that gives you a C value of 21. So now we have an A value and we have a C value. However, we need a B value for our equation. The way that we find that, the relationship in an ellipse of A, B, and C is that A squared minus B squared is equal to C squared. So therefore, you have A squared, which is 900. 30 times 30, minus b squared is equal to c squared, which is 21 times 21, which gives you 441. Solving this equation will give you a b squared value of 459. So therefore, b is the square root of 459. I'm going to leave it like that because all we have to do now is, since this is a horizontal, we're going to use this first equation again. We have x squared over a squared. A squared, here's a, 30 times 30 is 900. And then y squared over b squared, the square of a square root simply removes that square root, and that would be your window. Number 4, the entrance of a tunnel is in the shape of a half ellipse. Has a width of 40 feet, so the width would be from here to here. And a height of 25 feet at its center. So this goes up from here to here, 25. Now, since it's a half ellipse, if it were to go down further, that'd be 50 this way and 40 this way. So since this is longer, since it's taller than it is wide, that'd be a vertical ellipse. So we're going to use our second equation. Let me go ahead and box that in. So we have a width here. Since that's the b value, because it's not as wide as it is tall, we have a b value of, let's see, the width was 40, so that'd be a b value of 10. Or excuse me, width was 40, so that's a b value of 20. The a value would be the distance from the center to the top. That's going to be the height of that tunnel, which is 25. So there's your b and a values. And I believe that's all we need. Find the height of the tunnel 15 feet from its center. So that's a little bit tricky. Well, let's find the equation first, and then we'll talk about that. We're going to let this point right here, first off, that's going to be our center at 0, 0. So we have x squared over b squared plus y squared over a squared is equal to 1. There's my actual equation. So think about, how are we going to find the height 15 feet from the center? Okay, let me draw this a little bit better. Different color. So the width is 40 feet. So if this is the center right here, if this is 20 feet over, because the whole thing is 40 feet, well, what about if we went over not 20 feet, but we went over 15 feet? And we want to know how tall it is from there. Well, what in essence we're actually asked to do is pretty much just find what is this point right here. Because if our x value is 15, if we were to find our y value, that would tell us the height of the tunnel. So in order to find the height there, we're pretty much just plugging in 15 for x. So let's take our equation, take out our x value, and plug in 15. So you have 15 times 15, which is 225 over 400. Plus y squared over 625 is equal to 1. Move this over by subtracting, and you can find a common denominator there. Let's go ahead and reduce that though. That actually reduces to 9/16, and that's going to make our problem a little bit easier. So let's write that as 9/16. So I now have y squared over 625 is equal to 7/16. To get rid of our 625, let's multiply by 625, and that gives me y squared is equal to 273.44. Once we take the square root of that, and remember we would actually have two answers. The square root of 273.44 gives you plus and minus when you square root it. 16.5. And the reason it gives you a plus and minus is because if this were a complete ellipse, not only would there be a point here, but there would also be a point down here. That's the reason it's a positive and a negative. We're only concerned about the height, so we are only concerned with the positive 16.5. That's how tall this tunnel is at that point. Okay, number 5 says the planets travel in elliptical orbits with the sun at the focus. Be careful, sun is not the center, the sun is the focus. Mercury is 43.4 million miles from the sun at its farthest point and 28.5 million miles at its closest point. Find the eccentricity, and remember that's c over a, of the orbit and an equation to represent its path. Okay, so here's my elliptical orbit, and there's my focus there is the sun. So let's look at Mercury when it's at its closest point, which would be about right here. The distance from the closest point would be 28.5 million miles. And then when it's at its farthest point, which would be all the way over here, that's as far away as it gets from the sun, that's going to be 43.4 million miles away. So what we've actually got, since they gave us the closest and farthest point, I've just drawn the major axis. So the length of the major axis, if I were to add those two together, 43.4, 28.5, the length of the major axis is going to be, and I'm going to put major, that's going to be 71.9 million miles. The A value is going to be the distance from the center to one of the outside points on that major axis. So your A value is going to be half of that, which is going to be 35.95. Now, something else they've given you here is a C value. If you remember correctly, C is the distance from a focus to the center. So first off, let's find the center here. How far is it from there to here? Well, if it's 43.4 from here to here, and it's 28.5 from here to here, and we've also just found out that it's 35.95 from here to here. Well, let's just use those two numbers, 28.5 from here to here, 35.95 from here to here. If we take off the 28.5, that's going to be the distance from here to that focus. So 35.95 minus 28.5 gives you a value of 7.45. Now, A part says find the eccentricity, and we've actually got enough information now to find that eccentricity. The eccentricity of an ellipse is equal to C over A. So therefore, you have 7.45 over 35.95, which is about 1/5, or around 0.2 is what we're going to get. You get an eccentricity of 0.21. So there's A part. Now B part says let's find the equation for the orbit. So we have an A value and a C value. We're going to let the center be the point 0, 0. It's going to be the center of our orbit there, but we do need a B value. The way we find B values, and when we're talking about ellipses, is we know that A squared minus B squared is equal to C squared. Plug in this A and C value, and for B, you're going to get a value of somewhere around 35.17. However, as you're solving this, if you will just leave it as a B squared value, it's going to be more beneficial to us. So you're going to get a B squared value of 1236.9. And I'm just going to leave that as B squared, and you'll see why in just a second. Now this elliptical path, I've drawn it as a horizontal ellipse. So therefore, with the center at 0, 0, so that's going to be x squared over a squared. So we got to do 35.95 squared. That's going to be 1292.4025 plus y squared over. Now, this is the reason I just went ahead and left that as b squared. That's what you're going to plug into your formula anyway. 1236.9, and that is equal to 1. There's going to be the equation of that ellipse. Okay, number 6. With number 6, we're starting to talk about hyperbolas now. So let's go ahead and write down our two equations for hyperbolas. And I do want to remind you with a hyperbola, this first one's going to be horizontal because the x stuff is listed first. I do want to remind you on the bottom that a squared is always under the first term. Also, with a hyperbola, a is not always bigger than b. Sometimes b is bigger, sometimes a is bigger, so don't get that confused. But horizontal, the first one, vertical, the second one. If the x is listed first, it's horizontal. If y is first, it's vertical. A nuclear cooling tower is a hyperboloid, and you can see that the sides actually form a hyperbola. A hyperbola, and this is telling you what a hyperboloid is. It's a hyperbola rotated around a conjugate axis. So the conjugate axis would be right here in the middle. If you were to spin this around, it would form the shape that you're seeing here. So the tower has a diameter of 64 feet at its narrowest point. Now at the narrowest point, which would be right here, 64 feet, that'd be from vertex to vertex. So therefore, the distance between your two vertices, half of that is your A value, because from here to here, that's A, from here to here is A. So since the distance all the way across is 64, that means you have an A value of 32. At its narrowest point, and a distance of 116 feet between the two foci. So from focus to focus, here's a focus, here's another focus. If that whole distance is 116, well, the distance from there to the center is the C value. So you have a C value that's half of that, which would be 58. Also want to remind you that the relationship when you're dealing with hyperbolas between a, b, and c is that a squared plus b squared is equal to c squared. So we could very easily use that to find b, or why not just leave it as b squared? It's going to make it a little bit easier on you. Write an equation for the hyperbola. Now, since this cup's left and right, this is going to be a horizontal hyperbola, so we're going to list our x stuff first. We'll go ahead and let we'll go ahead and let this point right here in the middle just be 0, 0. That's your origin. So here we go. Since it's horizontal, you've got x squared over a squared minus y squared over b squared is equal to 1. And again, I just let this be 0, 0 so that we could do that. Your a squared value is going to be 32 times 32, which is 1,024. Now, we don't have b squared, but again, we can use this formula to find it. A squared, which we just found, which is 1,024, plus b squared is equal to c squared, which is 58 times 58, which is 3,364. Once you solve that, you'll get that b squared will have a value of 2340. And again, it's kind of silly to solve that for b, because in your formula, you need b squared. So go ahead and plug that 2340 in, and there is your hyperbola. Okay, number 7. Two ships located exactly 2 miles apart hear an explosion. Ship B hears the explosion 8 seconds after ship A hears it. If the difference in times that the ships hear the explosion is a constant on a hyperbola with the two ships at the foci, find the equation of the horizontal hyperbola, and they do tell us it's a horizontal hyperbola, on which the explosion is located. So the explosion occurs somewhere on this hyperbola. And there's some information that we're going to have about hyperbolas that we've not covered in the previous sections. So let me go ahead and draw these hyperbolas. The ships are located at the foci. And now let's go back and talk about the definition of what we mean by a hyperbola. A hyperbola is the set of all points, or the locus of points, to where this distance, which we call D1, and this distance, which we call D2, the difference is a constant. So D2 or D1 minus D2 is a constant. Now, we didn't tell what that constant was. That constant will always equal 2 times A. So that's some information that we need for this problem that we weren't given. Now, the ships here, it says the ships are 2 miles apart. However, down here we're talking about some feet. So instead of 2 miles, 2 miles is going to be, let's see, 1 mile is 5,280 feet. So 2 miles, let me come over here and write this, would equal 10,000, 5,060 feet. So therefore, there's the distance. So we're going to let this right here be the center. And the distance from here to here is 5,280. The distance from here to here is 5,280. If you don't remember, since the ship is at the focus, the distance from the center to a focus is your C value. So C in this problem is 5,280 feet. And again, I'm doing it in feet because this sound traveled down here at 1,100 feet per second. So let's do everything in feet. So let's try to figure out what our A value is, because we're going to need our A value to figure out what our equation is. So this, again, is going to be the information that we're going to need for our A. Now, it says that ship B, here's the explosion, 8 seconds. So that means that ship B over here must be further away from this explosion than ship A was. So this distance right here is going to be 1/8 of this distance. Okay, because it hears it 8 times, eight seconds afterwards. So therefore, the difference in the two ships' distances has to be, well, if it hears it 8 seconds afterwards, the sound travels 1,100 feet each second. So therefore, if you do 8 times 1,100, 8,800 feet must be the difference in the distances of the ship. Because again, this one heard it, and then 8 seconds later, this one heard it. So that therefore, again, in those 8 seconds that sound was traveling, it traveled this far. So therefore, that must be how much further ship B is away than ship A. So what do we mean by that? How much further? The distance that your ship B is minus the distance that your ship A is has to be a difference of 8,800 feet. And that's equal to, that distance will always equal 2A. So what we can do is now 2A is equal to that 8,800 feet. And that tells me that my A value is 4,400 feet. So now we're set. We've got pretty much all the information we need. So our A value is 4,400. Our B value is unknown, but our C value is 5,280, and we can use that information pretty much to very easily find B. We know with a hyperbola, A squared plus B squared is equal to C squared. So when we do that, we find out that our B value is going to be, actually, again, let's use our B squared value so we can plug it into our formula easier. It's going to be over 8 million, 8,518,400 feet. But again, that's our B squared value. And now we're ready to write our hyperbola, to write the equation. So let's erase this. Since it's a horizontal, we're going to list our x squared first. Minus, we're going to list our y squared second, and we're going to let, again, the point in between those two ships is going to be my origin right here at 0, 0. That way I don't have any transformations. So we have x squared over a squared. So we got to write 4,400 times 4,400, which is 19,360,000. Minus y squared over b squared. And I left this as b squared so to make it easier. That again was 8,518,400 is equal to 1. So there is your hyperbola. And again, that was all based on the fact, remember, that this distance minus this distance will always equal a constant 2a. Okay, number 8. With number 8, we'll start talking about parabolas. Now let's go ahead and write our two formulas for the parabolas. And there they are. Just a quick reminder, the y equals parabolas, cup up and down. The x equals cup left and right. If p is positive, the first parabola will cup up. If it's negative, it cups down. If p is positive, the second parabola cups right. If it's negative, it cups left. And then the h and k shifts your vertex of your parabola. Number 8 says a surveyor found a circular pond. So the top of the pond is circular. with a 36-foot diameter. So that's the actual width of the pond, but it has a cross section that's in the shape of a parabola. So the top is actually circular, but the actual pond goes down like this. And again, the top up here is circular. The distance across the pond is 36 feet. So there that is. In the middle of the pond, it is 12 feet deep. So there from the top down to the bottom, we have a 12-foot deep pond. How deep is the pond? 8 feet from the edge, round to the nearest foot. Okay, what we're going to do, we're going to identify some points on this parabola. We're going to let the surface right here, this is one way of working it. We're going to let the middle of our surface of our pond be the point 0, 0. And if we go down, that means our vertex here would be located at 0, negative 12. Negative 12, there we go. That means that we're going to have points on the right side and left side of the pond. If it's 36 feet across, that means this would be the point 18, 0, and this would be the point negative 18, 0. So we know that we are going to have a y equals parabola, and we also know that our p-value is going to be positive. So there's going to be y equals 1 over 4p, and we're not really sure what p is yet, but we do have a vertex located right here. So to go down 12 units and to go left or right 0, that's going to be the simple x squared. We don't need some parentheses there. And then we'll tack a minus 12 onto the end. So how do we find out a value for p? Well, one way of doing it is, and we've not done one like this before, but you can take any point on that parabola besides the vertex. That won't help. But we can take another point on that parabola, such as the 18, 0, and we can plug that in, and that's also going to tell us what our p-value is. So that tells us that when y is 0, that p is 18. So let's plug those values in, and let's simply solve that. And again, that's going to tell us what our p-value is. So we have 0 equals 18 times 18 is 324. So you have 1 over 4p, which would be 324 over 4p minus 12. We can clean that up, reduce that. That's going to be 81 over p. Move your 12 over. That gives you 81 over p is equal to 12. Move the p over, gives you 12p is 81. Divide by 12, and that tells you that you have a p-value of 6.75. So up here now in our equation, the only thing that we were lacking was that p-value, and it is a positive p. So let's go ahead and plug that in, and 4 times p is going to give you a value of 27. So now there's my equation of my parabola. And now let's see again what it's asking. How deep is the pond 8 feet from the edge? So 8 feet from the edge, so we're going to come in 8 feet here. So we need an x value right there to see what our y value is. If we come in 8 feet from here, that's going to be an x value of 10. So this is all the way out is 18. So therefore 8 feet in is an x value of 10. So now all we have to do, let me clean this up a little bit. So all we have to do now is plug in an x value of 10. So we're going to find y of 10. That's going to be 1 over 27 times 10 squared is 100 minus 12. 1 over 27 times 100 would be 100 over 27 minus 12. And I'm just going to type that in. That's going to give me a y value of about negative 8.3. So that's my y value when x is 10. So at x equals 10, we go down 8.3. So that's going to be how deep it is, about 8.3 feet deep. Okay, number 9, a cable connecting towers. The towers of a bridge is suspended in the shape of a parabola. The towers are 1,200 meters apart, stands to 120 meters above the roadway. The cables touch the road at the midpoint of the towers. Write an equation for the parabolic shape. So the biggest question is, where is the origin? So I'm going to work this slightly different from the way that the answer key is working it. So you've got some towers here and here that's connected by this cable here. The cable meets at the bottom right here, and now here's the way that the answer key works. That they let, like on that last problem, they let the origin be up here. However, I'm going to work it a little bit different. I'm going to let my origin be right here at the vertex. So that's going to be my 0, 0 is going to be the vertex. It's going to be the point where that cable comes down and touches the roadway. So my equation will be slightly different. As far as the parabolic shape, it will be identical, but mine will be translated. It has a different origin than what theirs does, so that's fine. So the cable connects. The towers are 1,200 meters apart. So that means the distance from here over to here is 1,200 meters, and they're 120 meters high, which means the distance from here up to here is 120. So let's find this point right here. If this whole distance is 1,200, then this distance will be 600. The distance up to here will be 120, so therefore this point is going to be the point 600, comma, 120. This would be the point negative 600, comma, 120. So let's go ahead and do the exact same thing we did on the last one, except for the nice thing here is since the vertex is located at 0, 0, we don't have to worry about H's and K's. So we have y equals 1 over 4p times x squared. No H's, no K's because this has not been translated any. The vertex is at 0, 0. So all we have to do to find a value of p is now take any point on this parabola, plug it in. So when y is 120, let me use a different color here. When y is 120, we have 120 equals 1 over 4p times x, which is 600 squared, and that's going to give me 360,000 whenever I square that. I can reduce the 4 and 360,000. That gives me 90,000. So that gives me 120 is equal to 90,000 over p. And I can solve that like a proportion if I'd like to. That'd be 1 times 90,000 divided by 120. So p would be 90,000 divided by 120. And you can reduce that if you'd like to, but you're going to get a p-value of 750. And now that I know my p-value, down here where I have 4 times p, I can now replace that with 4 times 750, which is 3,000. So y is equal to 1 over 3,000 times x squared. And again, my eccentricity would not change from if I let this be the origin or if I let the origin be up here. It's the same parabola, just translated up from where translated down from where, no, it would be up from where their parabola would be. Number 10, a satellite dish has a parabolic cross section, and we can see that right here. It is a parabola if you look at it from the side. The cross section is 20 feet wide at the opening. If the focus is 6 feet from the vertex, so you have this satellite dish, there we go, that at the opening is 20 feet wide, so the distance from here to an edge is going to be 10 feet, and the distance from there to an edge is going to be 10 feet. The whole distance is 20. The distance from the focus to the vertex is 6, so that's going to be your p-value. So we have a p-value of 6. Write an equation for the parabolic cross-section using the vertex at the origin. So that one, the last one didn't say anything about where to put the vertex, but it's going to be so much easier to let that vertex be the origin. So therefore, you have y is equal to, well, let's see if they want us to do, since it's turned sideways, they might want us to do an x equals. And they do. So your satellite dish looks something like this. This is going to be your origin here at 0, 0. Again, it's 20 feet across. The distance from the vertex to the, vertex of the focus is 6. Now, if I want to turn it left ways like this, I'm going to have to let my p be a negative 6 there. But since it's turned that way, you have x equals 1 over 4p times y squared. And again, you don't have to worry about any type of transformation. Since your vertex is your origin, we simply plug in that p-value, and you have x is equal to negative 1/24 y squared. So that's all you have to do to find the actual equation. So we found the equation. It says, then find the depth of the satellite dish at the vertex. So we want to know, how deep is it? How far is it from here to here at that vertex? So we know that this point, we've got to find some points right here. We do know those points there. It says is 20 feet across. So we know that the distance from here over to here, let's see, 20 feet wide. So that's going to be 20 feet from here to here. So that means that we have a y value right here of 10. We have a y value right here of negative 10. So this is going to be x comma 10, but we don't know that x value. That's what we're looking for is how deep is this parabola. So all we have to do to find out how deep it is plug in 10 for y. So therefore, we're going to take our equation and we're going to do x is equal to negative 1 over 24 times 10 to the second power, which is 100. So our x value there is going to be negative 1 over 24 times 100, which is going to be about negative 4.16. So this point right here on your parabola is negative 4.16 comma 10. So therefore, the depth is going to be about, you don't have to worry about the negative since you're talking about a measurement. It's going to be about 4.16, and that is in feet.